it's my pleasure to introduce Stephan Pfannerer, who is a postdoc here and obtained his PhD from TU Vienna under the supervision of Martin Ruby. And started here in September 2024 and actually worked for a software company on machine learning algorithms and automated document processing before that. So he has a very mysterious title here, and I'm excited to hear it. Thank you.
All right. Thank you for the introduction. So I'm very excited to give a talk here, and after the time I spent in industry, I'm very happy to be back to really abstract algebraic combinatorics and not thinking about machine learning anymore, although it's also very cool. It's very nice that I can kind of introduce me here to this department, because since September, I mostly figured out how to live here in Waterloo, and now I have the feeling that I finally settled down, so it's a good time to give a talk here. And my research usually is actually about webs these days, but if you were here a couple of weeks ago or months ago, Jessica Stryker, one of my collaborators, actually gave a talk on these webs that you have on my t-shirt, so a web talk is probably not the best to give today. So I came up with this very mysterious title, which is based on a research project that happened a couple of years ago together with Per Alexandersson, Martin Ruby, who was my PhD advisor, and Joachim Uhlin. And so now, I will not talk about webs, but I brought some other nice objects here. What are these? Chord diagrams, that's one way to put them. Another way to put them is these are non-crossing perfect matchings with 6 vertices. So in general, my research, I would say, is in the field of dynamical algebraic combinatorics. So we have dynamics, we have algebra, we have combinatorics. And so these are some of my combinatorial objects, non-crossing perfect matchings. This one here is actually not one non-crossing perfect matching, these are actually 2. So it's this one here, and also its rotation. If I rotate one more time, I get back where I started with. So already have some dynamics, we can rotate stuff. Or this one here, these are actually 3 matchings. This one, and this one. Okay. So we have combinatorial objects, we have dynamics. Here we have a slightly bigger picture. So non-crossing perfect matchings with 2 n vertices is that we depict the 2 n vertices in a cycle, and we make some chords in there so that they don't cross. And what I've been teaching, even last term, my students on Math 229, is that this is a Catalan object, so they're counted by the Catalan numbers 1 over n plus 1 times the central binomial coefficient 2n choose n. Okay, combinatorics, dynamics. Where's the algebra? For instance, here in polynomials. So what I like to do is to consider what is called a Q analog. A Q analog, what you do is you take an integer, and instead of the integer, you write some polynomial in Q, and when you plug in Q equals 1, you're supposed to get back the integer that you started with. So the Q analog of n is just 1 plus Q plus and so on, plus Q to the n minus 1, and when you plug in Q equals 1, you get 1 plus 1 plus 1 plus 1, giving you back n. There's also the Q analog of n factorial, which is just multiply the Q analogs of 1, 2, and so all the way to the Q analog of n. And we can also define a Q analog of the binomial coefficient as like taking the normal binomial coefficient and making the square brackets around everything. And it turns out actually that this is a polynomial in Q, which is kind of neat. And then we can, of course, also consider the Q analog of the Catalan numbers by just making square bracket around everything. And what's very cool, this again is a polynomial in Q, and it also actually has integer coefficients. So for instance, for C3, we get this polynomial here. Okay, so we started with some combinatorial object, we counted it, we made a polynomial out of this. And now, out of nowhere, let's do something weird. Let's evaluate this polynomial for some arbitrary reasons at roots of unity. And because we started with 6 vertices, it's a good idea to plug in a primitive 6th root of unity and powers of that one. And let's see what we get. Who is good at calculating with roots of unity? Okay, so the 6th one is a little bit tricky, but it turns out that this is 0. If I square it, I only get the third root of unity. That's a little bit easier because then the q to the 6 is 1, and then we have q squared plus q to the 3 plus q to the 4, and that's easy to see that this middle part cancels to be 0, and we get 1 plus 1 equals 2. Okay, I guess the second root of unity, minus 1, that's easy to plug in. We get 3. If we plug in xi to the 4, we get again 2. For xi to the 5, we get 0. And xi to the 6, yeah, plugging it 1. We already saw plugging it 1 into a q analog gives back the number that we started with. So we should get back the Catalan number 5 because we had 5 non-crossing perfect matchings. And wow, these are all integers. That's cool. And they're also non-negative integers. So there should be a meaning behind those. Okay. Let's do something that's not related to that, but rotate matchings. I already have told you, rotation is you kind of rotate them by 2 pi over 2n or pi over n. And we have 2 orbits for n equals 3. And now let's count the number of fixed points that we get when we rotate a bunch of times. So when I rotate once, there are no fixed points at all. 0. When I rotate twice, everything in this rotation orbit is a fixed point, so I get 2. Rotating 3 times, all of these give me fixed points, so we get 3. Rotating 4 times, we get 2 again. Rotating 5 times, no fixed points. Rotating 6 times is the same as not rotating at all. All of them are fixed points. Okay, mysterious, we have that these numbers match up. So there must be something behind it. And this is kind of a phenomenon that we see here. Because it's a phenomenon, it also got a name. It's a cyclic sieving phenomenon defined by Reiner, Stanton, and White. And so in general, what you have is you have a set X, a set of combinatorial objects, and you have some cyclic group action of order n on them, and you have some polynomial. And then you take a primitive n root of unity, and the definition is that you say a triple consisting of that set, the cyclic group action, and the polynomial exhibits the cyclic sieving phenomenon if what you just have observed is true. So applying the group action d times and counting the number of fixed points is the same as evaluating the polynomial at the primitive root of unity raised to the power d. And why is it called phenomenon? Well, it turns out that often the polynomial that you need to use is a q analog of the counting formula of that object for some magic reasons. And an example, I only claim it's true here, is the non-crossing perfect matchings with rotation and the q analog of the Catalan numbers. So the example that you've seen before, this is actually a general theorem that this is true. Okay, another object. Besides webs, I love standard Young tableau, and so this is not yet a standard Young tableau, this is a partition. This is the partition 4, 4, 2, 1, and I like to draw it in these Young diagrams where my rows, the number of boxes is weakly decreasing and all my boxes are left justified. And in combinatorics, when we have a diagram like this, we like to put in numbers, and the standard Young tableau is that we put in the numbers 1 to n in such a way that along the rows from left to right, for instance, the first one, 1, 2, 5, 10, this is increasing, and also along the columns, so for instance, the second column from top to bottom, 2, 5, 7, this is also increasing. And this is what we call a standard Young tableau of the shape given by the partition lambda. And in general, with S y t of lambda, I denote the set of all these standard Young tableau. Okay, so now we have another combinatorial object. And what we need to come up with maybe some cyclic sieving phenomenon is a counting formula. And there's a really, really cool counting formula for standard Young tableau, which is called the hook length formula. And for this, we need the so-called hook value. And maybe it's best to do it with a picture. So think of of your partition and a specific cell in there, and you want to define its hook value, think like I'm the cell here, or this is my cell, and then I have an arm length, and I have a leg length, and the hook value in total is the length of the arm plus the length of the leg plus 1 for the cell itself. Or here, for this cell, the arm here has a length 4, the leg has a length of 2 plus the cell itself. This is the hook length 7. And if I do it for all my cells, I get these bunch of numbers as my hook values. And the famous hook length formula to frame Robinson and Thrall from the 50s is that the number of standard Young tableaux can be calculated by n factorial, where n is the size of the tableau, divided by the product of all the hook lengths. And it's a really beautiful formula. And now that we have that, what was our next step when we have a counting formula? Yeah, find a Q analog of that one. Oh yeah, first I have the example. Okay, for this shape there are 450. Okay, we can do the Q analog by just making square brackets around everything. And here we have some additional correcting term that's, if you plug in 1 to this, you always get 1 because it's just the power of Q. And so we can mostly ignore it, but it's something that we unfortunately need to live with so that everything is actually working fine. Okay, so now we have an object, we have a counting formula, we have a polynomial coming from the counting formula. Now we need the dynamics. And for a standard Young tableau, there's a really famous bijection between standard Young tableau of the same shape, which is called Schützenberger promotion. And that one goes as follows. You may want to think of these numbers as like employees in a company, and 1 is the most important person and 11 is the least important person. And they have a weird way of arranging seats in there. And for some reason, number 1, the CEO, gets missing, so we need to promote all the other people to become better and to move on in kind of this tableau. So what we want to do is we want to kind of move around these numbers in such a way that we're still increasing along the rows and colors. So we want to promote everything up kind of one spot. So I deleted the 1, and then I can slide either left or up. But if I would, for instance, move the 3 up, that's not good because then the first row is 3, 2, 4, and 10. That's not increasing. So better move the 2. Or similar, now I have this empty spot. I can either move the 4 or the 5. What should I move? The 4, I can see that, yeah. Because if I move the 5 up, then the first row is not increasing again. Okay, next empty spot, what should I move? Yeah, 8. Why should I, if I move the 10, the first row is okay, but then the third column is not increasing anymore. So I better move the 8, and then I can only move the 11. I end up with an outer corner, so no more moves are possible. I fill this with the next possible value and subtract 1 from everything. And this, again, is a standard Young tableau of the same shape. And it's not so hard to see that this is actually a bijection between standard Young tableau, because the reverse is I can add 1 to everything, I delete the biggest thing, and then slide in the opposite direction all the way until I reach here, this corner. So there's an easy inverse map. Promotion itself is now the dynamics that we have. We have one way to produce from one standard Young tableau another one. It's like rotate those matchings. But the order of promotion, that can be very messy, except when we have a rectangular standard Young tableau. And rectangular standard Young tableau are beautiful because for those we know that the order of promotion is n. So if I apply promotion n times, I get back the tableau that I started with. And n being the size of the tableau, so the number of cells. Okay, so now we know that rectangular standard Young tableau are nice. So we have some dynamics, we have a polynomial, we have our family of combinatorial objects. And so there's this nice theorem which says if we have a rectangular partition, then the triple consisting of the standard Young tableau, the group action coming from promotion, and my F lambda, where I got rid again of this annoying Q power in front of it, that this actually exhibits the cyclic sieving phenomenon. And that was proved by Rhodes in 2010. Okay, let's do a simple example. If I take a rectangular partition with 2 rows, then it's not too hard to convince yourself that the hook length, so of size 2n, so with n boxes in the first, n boxes in the second row, that the hook values giving us an n factorial and an n plus 1 factorial. So we get this here as the Q analog. And have you seen that number before already today? No one? Yeah? Yeah, it's again the Q analog of the Catalan numbers. And we already have seen a cyclic sieving phenomenon with the Catalan numbers with our non-crossing perfect matchings. And it turns out this is actually the same cyclic sieving phenomenon because there's a bijection between the 2-row standard Young tableau of rectangular shape and non-crossing perfect matchings, such that this bijection intertwines promotion and rotation. So if I apply the bijection and rotate, I get the same as first applying promotion and then the bijection. Okay, that's kind of cool. I don't want to talk about the proof of that, but I want to prove something very different, but that's something that's motivated by this statement here. So one question that we can ask ourselves, so promotion is very bad if we don't have rectangular shape. What is this polynomial? Is this maybe still a good polynomial for some cyclic sieving phenomenon where we don't yet know what the group action is? So I want to talk now a little bit about what are the properties that the polynomial must have so that it can come actually from a cyclic sieving phenomenon. So how can we actually recognize a cyclic sieving phenomenon? We do need to have some polynomial with integer coefficients and some set with the only condition is that when we plug in 1 into my polynomial, we get the cardinality of that set. We want to have a primitive n-fold of unity, and if I plug in the powers, we should get some integers because it's supposed to count fixed points. And now the question is, are there some extra conditions that need to be satisfied for f so that we get a cyclic sieving phenomenon? And it turns out there's a really nice characterization due to Alexanderson and Amini from 2019 that if I have this setup, that there exists some cyclic group action, Cn, acting on X, so that we get an instance of the cyclic sieving phenomenon if and only if, for every k dividing n, this sum here is not negative. So what is that sum? Here is our f evaluated at the powers of the primitive root of unity, and this here is the number theoretic Möbius function. If you have not seen this, this basically takes the values 1, 0, and minus 1, and it tells you if a prime factor in the factorization of this integer appears more than once. Then you're 0, and otherwise you're 1 or minus 1, depending on the parity of how many prime factors you have. Okay, and so the situation, if you have a PhD student, and at the time of the project I was a PhD student, you have your favorite set X with some Q analog of the counting formula, and now you can ask your PhD student, hey, is there actually a cyclic sieving phenomenon involved with this polynomial? By simply checking this inequality for small cases, and then hopefully prove that this inequality is satisfied for all the cases that you want. Okay, So this is actually a really cool theorem, and I want to talk a little bit of where this sum is coming from. Okay, let's think again about the problem how we counted the number of fixed points. So when we counted the number of fixed points of rotation, let's say rotation squared, what we looked at is we didn't need to encounter this orbit here because it's an orbit of size 3. This cannot give us fixed points of rotating twice, but this one here can give. And in particular, we always get that a number of fixed points of rotation applied k times must be coming from all my elements of orbits in size d, where d is a divisor of k. Okay? And in number theory, if you have a formula like this, expressing the f's in terms of the o's, you can also express the o's in terms of the f's in some kind of inclusion-exclusion formula style formula, and that's basically Möbius inversion, where this Möbius function is actually coming from. So if you have this property here for all k, then you know that you can get OK from all my FDs in this way. And this here is precisely the sum that you've seen before. So the statement by Alexanderson and Amini basically means that all these sums here can count something, namely precisely the number of elements in orbits of size d. And that's why you want them to be non-negative. And in particular, when you have all your kind of orbit sizes given by that, you can kind of arbitrarily construct a cyclic group action by saying, oh yeah, let's take this bunch of elements and put it in this orbit, and this bunch of elements put it in this orbit, and this bunch of elements in this orbit, and this is how you can actually prove that you have the cyclic group action. But it's as good as saying, oh yeah, my two sets have the same cardinality, so I can construct a bijection by ordering them in some order and then mapping the first element to the first, the second to the second, and so on. So it tells us, yeah, there is this group action, but it's not a really canonical, not really good group action that we get by this. Okay. Let's go on. I told you about this research situation. You have your favorite polynomial, and you want to know, is it involved in a cyclic group action? And that's really what we did. We took our f lambda, and we asked ourselves, is it part, or can it come from some cyclic sieving phenomenon? And here is the statement, which is what I call the mystery group action, because we don't know what that group action is, but we know that there exists a cyclic group action of order n, where n is the size of the partition, which acts on pairs of standard Young tableau of shape lambda, such that we get an instance of the cyclic sieving phenomenon. So we have pairs of standard Young tableau of the same shape, we have some unknown group action, and we have our f lambda in here squared. And I really need to say we can really only prove the existence. We have only, for some hook shapes, we know, or we're able to construct such a group action in some nice way. And for lambda being rectangular, you can use promotion. And one thing that's a little bit different from the result by Brandon Rhodes is that now we have these squares here, and also here pairs of standard Young tableau. But actually, in the case where all these numbers are non-negative, you can actually drop all these squares and still get a theorem there. But we were actually, in particular, interested in really the square case, because when you see pairs of standard Young tableau of the same shape, if you're doing algebraic combinatorics, you should think of the Robinson-Shenstedt-Knuth correspondence. And that's why we were in particular interested in the square. Okay, I want to talk a little bit about the proof. So we basically want to apply Alexanderson and Amini. So we need to somehow evaluate this f lambda at the roots of unity and somehow need to show this inequality. And to tell you what these evaluations of f lambda at primitive roots of unity are, I want to talk about border strip tableau. So border strip tableau, they're kind of similar to standard Young tableau, but first you tile up your shape with strips of a certain length. And these strips are looking a little bit like snakes, so they start somewhere in the bottom and you can go up or right, but all these strips should be connected and don't contain like a 2x2 square in there. So you first tie it up with these strips, and then you fill in the numbers 1 up to the number of strips that you have. So here strip size is 3, and so I need to fill with 1, 2, 3, and 4 in such a way that if I read the labels from left to right in each row and also in each column, you're still increasing. So for instance, this third column here, I would read from top to bottom, this strip got the label 1, and then the next strip got the label 4. So we're still increasing. And here's another example of strip size 4. And why these border strip tableaux are really cool? Because there's a result that you can plug together by a result by Springer and Munaga-Nakayama, or the Munaga-Nakayama rule, which basically tells you if you take your f lambda and evaluate it at the dth power of an nth primitive root of unity, you get up to sign the number of border strip tableaux of shape lambda with the strip size coming from n divided by d. And here we can already see with these plus and minus that these values indeed can get negative, and that's mostly the reason why we put in the squares also in the theorem, so that we can get rid of these numbers, of the signs. And then we proved an inequality bounding the number of border strip tableau with a fixed strip size k. A lower bound for this is given by adding up all the numbers for border strip tableau where you consider strip size that are multiples of k. So for instance, if k equals 1, you get single cells. So here you would have the number of standard Young tableau. And this theorem says the number of standard Young tableau is bigger than the number of all the border strip tableau where I have a strip size strictly bigger than 1. But there are two exceptions of those where you have a shape that's just like a single strip, a horizontal or a vertical strip, because then you know that you always have exactly 1 and then 1 here and the sum of 1s over there, and that's then not working. But we can prove the inequality that I'm supposed to show you for these then in an extra case. Okay, so with this inequality, we can now show that the inequality in the theorem by Alexanderson and Armini is satisfied. So this is the inequality that we just had. Now we can also put squares in there and it's still valid. With the squares in here, we can use our f lambda evaluated at the roots of unity, because now we don't need to care about the signs, because the square eats the sign. Now we can sneak in these Möbius functions in there. Mu of 1 is 1, so here we are positive. And I told you that these Möbius values, they are only plus or minus 1 or 0. So by putting in some signs in here, I only make this part here smaller, or leave it the way as it is. And then I can write everything to one side. And this is precisely the inequality that we need to show to apply Alexanderson and Armini's result. And still open to finite group action. Are there any questions about that so far? Because then I can drink a sip of water. Okay. I promised not only a mystery group action, so a group action we know that exists, but we cannot find, but I also promised in the title a mystery statistic, and that's where we're going now. But one obvious question behind this theorem is, why should we actually care? Well, okay, we start with some polynomial, we plugged some values in there. Yeah, nice, we got something from there. And I said I'm doing algebraic dynamical algebraic combinatorics. So we have seen some kind of algebra because we had polynomials in there. But when I say algebra, what I really mean is representation theory. So where's the representation theory in here? And the main motivation behind this project comes from classical invariant theory. So we have some group, some matrix group, like the general linear group or the special linear group, SLR, and we have some representation, like the vector representation, the adjoint representation, whatever representation you care about. And then we're interested in taking this representation, taking a bunch of copies of that, so a tensor product of them, and still having G act on that tensor product. And then you want to know in classical invariant theory, what are the tensors that don't change by the group action? So we have some vector space here. And in algebraic combinatorics, when we have a vector space, we do want to find nice bases of that vector space. And what I mean with nice bases here is that I mean a basis that also respects some action of the symmetric group. So when you take your n tensor copies, you can always permute your tensor positions, and this gives you an action of the symmetric group. And this action commutes with the action of G on that tensor product. So there must also be some kind of nice basis that behaves nicely with respect to the symmetric group and on this invariant space. So we want to find a basis that's nice with that Sn action, and the best that we can actually hope for is to find a basis that respects the action of the long cycle. So the long cycle in Sn is you have 1 is mapping to 2, 2 is mapping to 3, 3 is mapping to 4, and then all the way to n, and then n mapping back to 1. And what this is doing on your tensor factors is it's taking your first tensor factor and puts it in the back. And we want to find some basis of that invariant space that's actually preserved by this action of the long cycle. So by taking the first tensor position and put it in the back. And this movement with my hand, this already is kind of like rotating. So what we really want as a nice basis is a basis in terms of pictures. So we don't want to have some weird polynomials. We want to draw pictures that give us a basis of that invariant space. And in the beginning, I kind of promised that I will not talk about webs, but now I talk about webs. So for SLR, for R equals 2, the solution is what I would call an SL2 web, but you have seen those. These are the non-crossing perfect matchings. These give us a nice basis of that invariant space. For R equals 3, it's the basis given by Kuperberg's webs. And for R equals 4, this is recent work together with a bunch of collaborators, is what we call the hourglass playback graphs and the SL4 web. Basically, that's what's depicted on my t-shirt here. Okay, but that's enough of the web talk. What's going on with GLR and the adjoint representation? It turns out when I have R bigger than n, so R is the dimension here of the vector space, and n is how many tensor factors I take together. It turns out when R is bigger than n that I can use permutations, at least as an indexing set of my bases. And this action of the long cycle then on the permutations, for this I need to again draw my permutations in some kind of chord diagram where I have my vertices 1 to n in a cycle. And if I maps to j in my permutation, I make some chord directed from I to j. And then rotation of that permutation is take that picture and rotate it. Or in terms of some algebraic expression, it's you conjugate with the long cycle. Okay, so this statement here is true for R greater or equal to n. And now the question is, if we make R smaller than n, can we still say something there? is there maybe some subset of permutations that I can use to get a nice basis? And that's actually where this mystery statistic is coming from. So we were able to show, and this looks very different from the theorem that we had before, but I will tell you how those relate, that there exists some statistic, and with statistic I mean some kind of weight function where my weights are not necessarily integers, but here they are partitions of size n. So a map from permutations to partitions such that the cardinality of all my permutations getting the statistic value lambda is given by the number of standard Young tableau of shape lambda squared. So this is the first property, and moreover that statistic is preserved by rotation. So if I rotate my permutation, I get again the same statistic value. And when you have a statistic like this, oh yeah, we can only prove the existence of this statistic, so it's like this mystery statistic. But when you have a statistic like this, you can construct a set S and R where you choose those permutations that have a statistic value where the partition has at most R rows. You collect those together, and then it turns out that a set S and R like this must give you a rotation invariant basis for the invariant space for the adjoint representation. And so that's why we really care about it. On my last slide, I'm a little bit fast in time. I want to talk why this theorem actually comes from the mystery group action. And it's a very vague sketch that I'm going to do here. So we have first a result again by rows that we need to use. Namely, that if I take all my permutations together with this cyclic group action of rotation, and I take the sum of all my f lambda q squared by sum over all lambda, that this is an instance of the cyclic sieving phenomenon. In terms of representation theory, one way to express this would be saying, oh yeah, Sn carries the action of some cyclic group such that this here is my character. Or maybe put differently, we can make Sn into a module for a Cn representation. Now we have learned that f lambda q squared always gives me a cyclic sieving phenomenon for some group action that I don't know. But this somehow tells me that this is what we can see or think of as the character of my representation must decompose into smaller characters. And when you know that a character decomposes, you know that also your representation decomposes into smaller representations. And so when we decompose an Sn, this decomposition really tells us this is the statistic value. And that's all that I want to say. Thank you.
Thank you. If there's any questions, please wait for the mic.
Yeah.
So for your proof of the existence of the mystery statistic, you use the mystery group action. If someone were to find this mystery group action, would that then give you what the mystery statistic is, or would that still be another hard problem?
I guess we would be, that's a good question. I guess we would be able to somehow construct it then.
Okay.
At least I'm very positive that we would be able to do that. Actually, we tried harder to really with directly coming up with that statistic. And we were not lucky at all with that. So I would say it's actually probably better to try to find the statistic and from the statistic then get the group action. Because this seems to be more attackable, but we failed so far. So.
Okay.
So there's a question by Olia.
I wanted to ask about how you tried coming up with statistics. Did you have some systematic method for that?
That's an excellent question. So I'm a huge fan of Sage. And there's a Sage package since Sage 10 that's called bijectionist. And bijectionist, what you can do is you can put in a bunch of constraints, like you want to find bijections, but also statistics that you want to be preserved by some group actions, and then you plug all these in, and then you hit enter, and then the computer will translate it into a mixed integer linear program and try to solve that and give you candidates for that. And then you want to try to restrict the problem even further by saying, oh yeah, we don't only want to have like that the statistic is equidistributed with what I would call Robinson-Shenstedt shape, but maybe we want to have some companion statistics with which you have done some tuples that are equidistributed, and you hit it in the computer and ask the computer, do we find something? And at some point you hope that you can guess the pattern, but we never were able to guess the pattern. And the reason actually why this bijections package in Sage exists is because we developed it just to find that statistic. And yeah, we still don't know that statistic. And then another systematic way to try to find it is to use this awesome statistical or combinatorial database of statistical or combinatorial statistics, this is what I want to say, which is called FindStat. Really cool tool. So you get some idea of a statistic, and you it's like the online encyclopedia of integer sequences. You have your combinatorial objects, you have a bunch of values, and then you hit the search button and can try to find if something in there fits what you put in there. And FindStat doesn't find anything in there. And one of the reasons why FindStat exists is this problem, actually. So this problem at least motivated my advisor to write together with me and others a bunch of amazing code, and that's usable for other stuff. But unfortunately, not to find it. And actually, the project came along we tried to find that statistic really hard. And at some point, I told Martin, let's try this stuff to prove that this stuff actually exists. Maybe we can do that. And then at least know that our search is not for nothing. So.
Do you think there's actually a nice answer that you're missing, or do you think it's just something horrible?
That's a really good question. To be honest, I don't know. So the computer spits out really many possibilities as possible statistic values, and it's simply, at least for me, it's not restricted enough to see patterns in there. One thing that I do want to try, but never had the time to try, to use actually some machine learning techniques to maybe train a neural network to magically spit out a fitting statistic. And then use some cool techniques to maybe look into the neural network to see what are the defining properties that they have in there. That could be a hope, but so far I haven't tried that.
What's kind of the order, the number of candidates you have? Like if you put in the most restrictions, do you have like hundreds of candidates for bijections, or thousands, or tens of thousands?
I cannot really tell, because I don't know. It's a bunch of years since the last time really looked at that.
Can you go back to the promotion page with the polynomial? Yes, here's. I was wondering what the kappa is on the.
Okay, so here I multiplied the kappa away. Here is the kappa. So what it is, you take your conjugate partition, and then have some parts. Let's call them lambda 1 prime, lambda 2 prime, and so on. And you take lambda I prime, choose 2, sum of all I. That's kappa of lambda. But you shouldn't care about it. It's just some normalization factor.
Have you heard of the LODA language, and have you looked at applying that to find the statistic?
I haven't heard about that, but I will look into that. Thank you.
So it like lets you search for a small program that outputs some certain sequence.
Okay.
So maybe useful.
Thank you.
If there's no more questions, let's thank Stephan again.